Okay, so what I'd like to talk about is Understanding Infinity by Anthony Gardiner. A very nice book about why calculus works. So I know a lot of times when you're taking calculus, you don't really get why all of this stuff is working. It's partially because you're just getting used to the idea that you can do weird things with functions. Um, and you've got all of these processes you have to learn about. You have to learn about how to do differentiation. You have to learn about integration. You have to learn about these series and these limits and all these things. And the really interesting thing that's at the bottom of calculus is this infinity thing. It's very, very interesting, this infinity thing. And, it's good to get a little bit of learning in about it. And this book by Anthony Gardiner is a very good way to do that. It actually gives you some idea about what it is all this calculus stuff is actually doing. And I liked it very, very much. I think when I read this last, I did get a pretty good idea from some of the stuff it was talking about on how to try to do computing with real numbers. Unfortunately, I went through and I looked up some papers and found out there's something called computable analysis or computational analysis. I'll bring the book by sometime to share that with you. But there's already a sort of branch of analysis that deals with computing with real numbers. It's really quite awesome. But that's not what this book is about. This book is just something that is, I'd say, maybe between um, calculus and analysis. So something that somebody who's taking a regular calculus course or has taken just the first year of calculus course could use to give them a stronger idea about what all that calculus stuff is about, and isn't quite as involved as your regular old epsilon delta advanced calculus or real analysis courses. So let's take a peek at this. I do like, well, obviously, I love the beginning of this chapter, What's Wrong with Calculus? Um, but I also like, right here in the advice to the reader section, it may be necessary to stress that the exercises are an integral part of the text. That is, before you go on to chapter 2.4, you might want to at least try the things that are going on in 2.3. I normally, when I'm reading a book and doing the problems at the same time, I'm usually reading a couple chapters ahead of where I'm currently doing the problems. But you should try to make sure that you're not getting too far ahead, because once you get down here to the last chapter, if you're way down here, you're probably going to stop. So you don't want to get too far ahead with your reading compared to where you're doing your work with the um, problems. That's really important also because, chapter 2.12 literally is going to care about what's going on with all of these different things going on behind you, right? So really, you should have a good knowledge of what's going on in 2.9 before you're doing 2.12. And you don't really know about how well you're doing until you've actually done the problems, right? Why is that? Why is that? Well, it turns out that if you don't understand something, you don't know that you don't understand it. That's really the um, crux, right? The point where you start understanding something is where you start understanding that you don't understand it. That's the beginning point of you starting to understand something. Um, Obviously, after you've gone through it and you have some acuity and you know it, that's a little bit different. But at the very beginning, um, you don't even know that you don't understand something sometimes. So the book is set up in 4 parts, from calculus to analysis, the idea of number, some geometry stuff, and some function stuff. Um, a lot of this is really just talking about what is a number, right? What is a number? What's going on with it? And I guess I should have done some additional stuff down here, but c'est la vie, right? I didn't read anything extra down there this time. It's been a long time since I read through it and took notes, so this is about the way I was taking notes 2014 and earlier. Well, 2010 to 2014. Before 2010, I wouldn't have kept things in the book. At some point, I just decided it was easier to leave the notes in the book. Although I've had this book for longer than that, so I did work through it, or did look at it, read some of it previously to actually reading through the entire book earlier on. Um, let's see. So, from calculus to analysis, this is talking about from going from basically what you did in your freshman year of college to what you might do in your senior year of college or your freshman or your first year, not freshman year, of graduate school. Right. Calculus is basically learning how to do calculus, right? Learning how to take derivatives and integrals and series and things like that. Learning how to take this one function and turn it into this other function for a particular purpose. Whereas analysis is trying to explain why calculus works. And that's what's wrong with the calculus, right? It's not what's wrong with calculus today. This is sort of the issue of why didn't they have a good foundation for calculus early on, right? When Newton started with his calculus, he didn't really justify it too much. Actually, Leibniz did a better job of justifying it, only the monads didn't really work out very well. The monads didn't work out very well. Although Abraham Robinson in this book, Non-Standard Analysis, well, maybe in papers, but this field, non-standard analysis, that's basically a calculus with monads, with infinitesimals, right? Infinitesimals don't exist really um, in these proofs, this sort of analysis proofs that we've done. Um, and there are a couple of reasons why that was. One, it worked. There was no reason after you got this thing working to sort of figure out the reasons why. You could think of reasons why, but it wasn't that important. There was a lot of work to be done in just figuring out how to do things for quite a long time, for a couple of 100 years. And it really not until about the 1850s did people really start doing mathematics the way mathematicians do mathematics now, right? With the theorems and the proofs, and when you get into analysis a little bit later, not that much later after they started doing proofs, all the epsilons and deltas and weird things. And so there wasn't a reason for it. People weren't really doing that kind of proof at that time. They had to move on to that at some point and do something that was completely justified. That's what mathematics is. It's mathematics is done today is about, is really being justified in every step that you take. But they had really good reasons, right? They just weren't mathematical reasons. They just weren't real proofs that were indubitable, right? That's what mathematics is about now. Um, Growth and change in mathematics. Well, what he's going to talk about here is different kinds of numbers. What is a negative number? What is a complex number? What is a rational number? What is an irrational number? Who knows? Those are all crazy things. And then he goes into this, right? So we talk about mathematics, rational or irrational. Um, oh, I'm thinking. I mean, I just looked at this. Yeah, so this is really about rational and irrational numbers. Numbers that can terminate, right? As far as those decimal representations are concerned here. Rational numbers, right? You'll remember can be presented as ratios of integers, right? Irrational numbers are everything else. there are a couple of big important things about these two things. One of these big important things is that irrational numbers cannot be constructed that way. Irrational numbers, though, show up because of ideas like squaring things, right? You know, if you have a number 2, what number squared gives you 2? It's the square root of 2. Yes, we know that. We know that it's irrational, right? If you have a circle, the ratio of the diameter to the circumference of the circle is pi, which we also know is irrational. But those two numbers have to exist since there are circles. Those things end up being irrational. The strange thing is not that there are more irrational numbers than rational numbers. That makes a lot of sense because does it make sense? Actually, I'm not sure. Does it make sense? I know that it's true, and I know why it's true. But does it make sense that it has to be that way? Why can't there be a 1-to-1 ratio, right? In the real numbers, for every rational number in between, there has to be at least, there's going to only be one irrational number between any two rational numbers. Why is that? So I can understand why there always has to be another irrational number, but I can't understand why there has to be an infinite number more than that, except that there's certain proofs that I've seen. But I can't think of a reason why if you just came on that. What I'm trying to say is, if somebody just asked you, must there be more rational numbers than rational numbers? I don't see why there'd be an obvious reason for that if you haven't been through, this analysis class. Although it's completely true. There are weirder things, right? The rational numbers are so much larger than the rational numbers that it's a completely different infinity than the rational numbers. So the rational numbers have one infinity, the irrational numbers have a larger infinity of things. So not only are there more irrational numbers than rational numbers, there are infinitely more irrational numbers than rational numbers. It's really awesome. This is called a continuum. This is called a countable infinity. This gets us to this really weird idea, which is that there are just as many rational numbers as there are integers, right? Or positive integers, or whatever you want to say. That's really weird because the integers inside of the rational numbers, you can write each integer as itself divided by 1. That's one kind of rational number. Well, obviously, there are an infinite number of more rational numbers than there are numbers, right? There are counting numbers. But still, the total size of the sets is the same. And that's something you'd find out in analysis. I don't think we really talk about that. He really talks about that in this book. That's not what I remember from this book, but that's one of these cool things that you get from analysis, is that there is a proof that shows that for every rational number, you can do this sort of mathematical trick and turn it into a counting number, so that you can do a 1-to-1 correspondence between rational and counting numbers. It's very counterintuitive. Again, that makes the thing I was talking about with the why are there even more irrational numbers than rational numbers, right? There are more irrational numbers than there are rational numbers, even more irrational numbers than there are rational numbers, than there are rational numbers, more rational numbers to counting numbers, 1, 2, 3, to infinity. That's a little bit insane, and it's absolutely true. And, I can talk about it here and there, but it all comes down to these non-constructive methods in mathematics, right? You have to be able to show sort of obtusely, obliquely, let's say, not obtusely, let's say obliquely, something like that, right? That would be a very logical way of going about things. That might not give you a lot of insight for what's going on. Now, if you can do a construction for something, that is going to be something that gives you a lot of intuition about what's going on. But it might not be very, very general, and there aren't that many things that you can do that are completely constructive. Let's say that you can build up a really solid proof, a really solid rationale that nobody can doubt just by creating some sort of construction. They're very important constructions in mathematics, but these non-constructive methods, these purely logical methods, become much more important as you go on in mathematics. This particular chapter is about saying, when you do this calculus stuff as an undergraduate in your freshman year, right, when you're doing your freshman calculus sequence, this stuff is all basically constructive. In fact, he calls it sort of naive constructivism. It is so simple, right? Or maybe I shouldn't say simple, but it is presented in a way where it's just you learning to do the stuff, right? There isn't very much. There is some if you read the books, but there isn't very much sitting around showing you why in a mathematical way, this non-constructive method, that the things are true. That's what these real analysis courses are for, showing you the deep truth behind them. But there are more constructive methods that are still better than just this naive approach that you get in your freshman year of college. Let's see, when we get to common measures, this is sort of this weird thing, right? When you start off thinking about how to measure things, right? You'd say, okay, well, this Sharpie is 1, 2, 3, 1, 2, oh, it's a little bit more than 2 and a little bit less than 3 caps wide. It's easy to have a idea about measuring when your standard 1, 2, 3, 4, 5, 6, 7, 8, 10, 11 is exactly perfect for constructing your length, right? So you'd say the Sharpie is 11 dice long, which is really, really interesting. Well, it's not interesting, but that's how in physics, for example, I'd present how do you measure something. Well, you have a standard, this die, and the Sharpie is however many dice long. If you have a system where this guy is, the Sharpie is exactly 2.5 caps large, we could use, say, a half cap as our measurement standard. And then we'd say the cap is 2 half caps long. The Sharpie is 5 half caps long. That's easy to talk about, right? We have these common measures, and as long as we have something that's rational, like that, right, that we can make another measure even if the measures don't coincide, right? Even if the numbers don't coincide, this guy here and that guy here, this is 2 and this is 2.5, we can make another measure, which is halves, where this is 2 of those half caps and this is 5 of those half caps. So we can make a common measure, and we have a common factor and so forth and so on. But we end up with a problem, right? Sides and diagonals of regular polygons, I don't have to tell you about the square root of 2 and the square, right? The diagonal of a square. That gives us some major headaches as far as measurement is concerned, because there is no common measure for the diagonal of a square and the sides of the square. There's no common measure for the diameter of a circle and the circumference of a circle. And why is that? Well, the reason is pi and the square root of 2 are irrational. So that's a very interesting way to think about things, right? So now we know that this naive idea that we have about numbers does not work for diagonals and circles and things like that. And actually, there's no good reason for this, but I'm going to say that the people who think that You should change pi. Should think again, right? I don't remember what Greek letter they called it, but here we have their circumference is equal to pi times the diameter. This is perfect. Some people want to use the radius. That's fine. It's okay to use the radius, but let's say I'm going to measure the diameter. Well, I can just measure the diameter, right? I can do that. I can use a caliper to measure that diameter, right? However, I measure the circle, this the circumference maybe with a string coming around like that. I can measure the circumference. I can measure this. I can measure that. The radius, I can't measure any stupid radius. If I'm lucky, there might be something that's purportedly at the center of the circle that I could maybe use the calipers for, depending on what actually is going on. But then you need something where, yeah, I can't really do that very well. Maybe I could if there was like a half thing cut out here. But otherwise, you can't really measure the radius. What you have to do is you have to get a good idea about the diameter. So anybody who complains about pi, they're morons, especially on YouTube, because people who upload things to YouTube are morons. And I got that. I get the irony. Okay, I wouldn't have said it if there was no irony. Okay, and then there's a little review of arithmetic and numbers. Then we start talking about the problems with infinite decimals. And that is, how can you add infinite decimals? What are they anyway? All we know about them is that they're between two other numbers, right? And as you get closer and closer and closer and closer to them, we just reduce the distance between those two rational numbers, right? We're not really getting anything super new with the infinite decimals. They're really complicated. They're a hard thing to understand, even when they're still just these recurring nines, right? A lot of interesting things with the recurring nines. And then we get to fractions and recurring decimals. Some fractions, we know, get the strange things like in the recurring nines. But at some point, we have to get to real numbers, right? Here, we're still dealing with these irrational numbers. Now we're still dealing with rational numbers. Now we're dealing with irrational numbers, right? And this is where life starts to get fun, okay? And then we have this arithmetic of infinite decimals and so on. I think it was in here I got that idea about what to do with adding real numbers in the computer, how to deal with it. But how far did it actually go? I think, oh no, maybe it was a little bit later on because it had to do with continued fractions. So, but in any event, the continued fractions in some way allow you to compute with real numbers, and you can think about how to do that. It's actually quite interesting. So we've talked about this. This gives us some ideas about all of these really cool infinite things that we've been talking about. Then we go to geometry. What's going on with geometry? How do we use geometrical intuition? And then we get into comparing areas, volumes, curves, and surfaces. And that is something that is really hard, right? That's really hard for students to get the first time they see it. I am certainly one of the people who enjoy these things quite a lot. And I just assigned some stuff earlier. And it's not really hard, right? This is sort of the idea, right? I can bound this curve, right, with between here 10 and 4 of these boxes. Then I can do a finer mesh, and I get a finer and finer and finer mesh, and I can bound the size of this curve between the external boxes and the boxes that just peek a little bit outside of the curve, and the boxes that are fully inside of the curve, right? And as I get a finer and finer and finer mesh, right, I come to the actual area, right, of this funny looking curve. And the analytic way we do that is we call that an integral, right? That is what an integral is, right? Is finding that area. And there are different ways to do it. And here are some interesting things with different areas and stuff like that. The sort of things you need to think about when you're comparing volumes and or comparing areas and volumes and things like that. Let me see. Do they have? They do not have any of the fun things. This does have one of the interesting problems, one of the more interesting problems, which is when you slice things up, right? What do you end up getting right here? I think this is just doing volumes. Maybe this one doesn't. Maybe there's another book that's very similar looking to this that has a lot of series stuff in it that I own. Also, I think by Dover. And that one probably has the tower that I'm thinking about that never quite falls, although you really, really think it should. And then we get into functions and what is this stupid function thing anyway? And you had to go through all this stuff to figure out what these functions are and even what that scary exponential function is. And that is the end of that book, right? When you start getting in here, right? We have this reprise of what is a number, right? We've been through all of this already. We have this reprise, and it's good to have that reprise. These weird things with functions, that's very important to have an idea about what those functions are and how to use them for different things. And then you're done, and it's very nice, a very nice thing. $20 when I bought this. I have no idea when um, this came out in 2002, so um, well after I'd been through all of those classes I was talking about. Well, this did. This is actually a 1982 book that was reprinted in 2002, but I'm sure I wouldn't have bought this book for $75 or $150 or whatever it would have been in today's dollars back then. No matter how cool looking it is, it's perfect. This book is perfect for somebody who's just been through that first calculus course or one or two calculus courses and wants to really understand what it is they've done, really wants to get a good solid feeling about what they've done and wants to solidify what they've done. And that's a really a good thing, you know, in that summer after you've first done calculus, going through and working through this, you know, would be really good, especially if you're going to be in physics, math, or engineering, because this book, this kind of book, is really, really good for strengthening your skills for later, right? It's, I mean, I would have loved to have a class like this available when I was an undergraduate, but I took way too many classes. I mean, I took basically um, an extra year, year and a half of classes. Is that it? Yeah, an extra year, year and a half of classes, uh, because you know I went to school at night and I always had to take a class, right? I was worried that if I ever stopped taking any classes, I would stop going. But when you're going to school at night, you only get the classes that are available at night, so they don't always work out. So I ended up with a lot of excess classes. Um, Again, I would say this is a wonderful book for you if you want to, you know, get an idea about things. Like a lot of the books I've recommended that are undergraduate level, this is sitting halfway in between that first year and that senior year in its difficulty, so that it's a really great way to um, bridge between the that lower division and that upper division coursework, because there is a real sort of shift in physics and mathematics where I've done this stuff. There's a big shift in the way you're supposed to think from those first 2 years to those last 2 years. And it's a good idea to try to initiate that shift a little bit early. Okay. And this is exactly the kind of book that's good for that. If, like me, you've been through all of these things before, this is just a fun project book, right? Um, if you've got your bachelor's in mathematics or in physics or in engineering, and you just want to have a little bit of fun with math, if you're the kind of person that has fun with math, this also is a really great book because it is a fun book to read, and the problems are reasonably interesting. So again, this is a good book. Now again, as he said, these books or these exercises here, where are they? These exercises are sort of built in with the text. So if you should have a good idea about how to do this. I think at least one time, this is exactly the sort of thing where having some Excel skills are good. So at least once I got, a little bit, how should I say? This was sometimes a book has like a first problem that doesn't stump you. It's just a little bit too much work. And without Excel or something, this calculation is, for example, too difficult. So if you're like me and like to work these little problems alone, you know, sitting around in a coffee shop or something away from a computer, then, like when I ran into this, I had a problem. There's another book that had that same issue. Yeah, I think I've already looked at this one. So like this Lawton book with tensor calculus, this first problem, again, this one's a little complicated to really start off with, but if you can do it, then you're ready for the rest of the problems in the book. That happens sometimes, right? They are technically review. I mean, the one I was just showing you, it's not a big problem, but I'm not going to do a 50, a 50 term sum by hand, right? Maybe as an undergraduate I would, but now, I want to use Excel or program it or something like that because it's just not worth it doing it by hand once you understand how to do the sums already, right? So there are a lot of things like that. There aren't very many problems like that, but occasionally you run into issues. Um, so again, I think this is a fun little book to work through. You can see the math is not super hard. It's mostly just describing what you're doing. It's got some interesting things like Greek alphabet, Roman numerals, things like that. But for the most part, it's reasonably doable, I think. So, um, good recommendation for people sort of halfway between their their lower division and upper division classes in mathematics. Also, I think it's a very good book for people who've finished with school, but really like cool things like infinity. Infinity is awesome. Um, and this is a really nice book to get you understanding what all that stupid calculus stuff was really about anyway.